In this video, we are going to do a sample problem for graphing simple harmonic motion. And these equations that I've put up here are all directly from the official AP equation sheet, and they are the only equations you'll need to use for this problem and hopefully most of these types of problems. So we have an object of mass 0.8 kilograms is attached to an ideal horizontal spring that has a spring constant of 180 newtons per meter. The block is set into oscillation on a surface where friction is negligible. Its amplitude is 10 centimeters. We want to find A, the period, B, the frequency, and C, the angular frequency. We then want to express the position of the block as a function of time. We want to plot the position as a function of time, and we want to sketch the velocity and acceleration as functions of time. So the first thing we want to do is find the period, and the period for a mass on a spring is this one right here. So it's T sub S for spring equals 2 pi times m over k, where m is the mass and k is the spring constant. So we're going to say that T is equal to 2 pi times the square root of the mass, which is 0.8, over k, which is 180. And if you plug all of that into your calculator, you should get that it is equal to 0.419 seconds. So this is our answer to part A. And then for part B, we want to find the frequency. And we've got this equation here, which tells us that the period is the inverse of the frequency. So that means the frequency must be the inverse of the period. So F is equal to 1 over the period, which is equal to 1 over 0.419. And you can just press that nice inverse button on your calculator, and that would be equal to 2.387, which the units there are hertz. So that's our answer to part B. And then for part C, we want to find the angular frequency, which is symbolized by omega. So we know that 1 over F is equal to 2 pi over omega, and let's cross multiply there. So we've got that omega is equal to 2 pi times the regular frequency. So C, we're going to say that omega is equal to 2 pi times 2.387, which is equal to 15. And the units there are radians per second. Now for part D, we want to express the position of the block as a function of time. So for that, we want to use this equation here, where remember A is the amplitude, and then we've got the cosine of 2 pi times the regular frequency times t. So our amplitude is 10 centimeters, which we want to convert to meters, so that's 0.1 meters. Then it's going to be 2 pi times 2.387 t. And we actually already did 2 pi times 2.387 to get our angular frequency. So this is our expression for position as a function of time. Now we actually want to plot position as a function of time. So I want a little bit more space for that. So I'm going to draw some axes here. Now my amplitude is 0.1. So that means the maximum that my mass is going to go to in terms of position is 0.1. So I'm going to label that as 0.1, and the absolute minimum value it'll get to is negative 0.1. And I also know that my period is 0.419 seconds, which I'll just round down to 0.4, so it's a little bit easier to draw. So that means I know it has to do one full cycle. So return to its original position in around 0.4 seconds. Remember, my period over here was 0.419 seconds. So what that means is it's going to be at its minimum position in half that time, so around 0.2 seconds, and half of that will be when it's at its equilibrium position. So that'll be at around 0.1 second. So I'm going to go by 0.1s for my time axis here as well. And I'd like to show 2 full cycles, so I'm going all the way out to 0.8 seconds. So label my axes, time is in seconds, position is in meters, and then I'm going to use a different color to actually sketch the graph. So this is a cosine function, which means that if I plugged in 0 for t, my initial position is going to be at this maximum amplitude of 0.1. So I want to start by plotting it there. And then, like I said earlier, I know it's going to be at equilibrium in a quarter of the time it takes to get back to its original position. So that's going to be at around 0.1 second. And then at around 0.2 seconds, it's going to be at its negative amplitude. And then back at 0.3 seconds, it's going to be back at equilibrium. And at around 0.4 seconds, it's going to be back at its original position. And it'll do that for another full cycle. So it's going to look like something like that. And that pretty much looks like a cosine curve. I feel like I did a pretty good job. So that is plotting my position as a function of time. So as we can see here, it takes this full amount of time to go back to its original position, and the maximum it gets to is 0.1, and the minimum it gets to is negative 0.1. Okay, so now we want to sketch the velocity and acceleration as functions of time. So I'm going to use the same scale that I used before, at least for time. And this is going to be velocity, which is in meters per second, and then the time, which is in seconds. So I'm not going to worry about labeling my y-axis here because it does say to sketch. The only reason that should be 0.8. The only reason I labeled my x-axis here is because I wanted it to be on the same scale in terms of time as the position function. So for velocity, well, remember that when the amplitude is, or when the object is at its maximum position, the velocity is going to be 0. And let's just make that our max and min. It's going to be, remember, 90 degrees out of phase. So I know it's going to be at its negative maximum there, back at equilibrium here, and it'll be back at 0 at 0.4, and then back at 0 at 0.8. So that is going to look like something like that. So it's out of sync with the position function, but it follows a similar pattern. Lastly, let's sketch our acceleration as a function of time. We still want to do that same scale. Now, when the position is at a maximum, so it's positive maximum, the acceleration is at its negative maximum. So the acceleration function is going to start out here, and then after 0.1 second, it's going to be 0. After 0.2 seconds, it's going to be at its positive maximum. After 0.3 seconds, it's going to be at its negative max, or back at 0, negative maximum again. And remember, the 0.4 seconds is for a full cycle because that's the period. And then it'll be back at its negative maximum at 0.8. So that is going to look something like that. So notice that the acceleration, which I should label there, and the position functions are exact opposites to each other, whereas the velocity function is 90 degrees out of phase with both of them. Okay, so there's actually another little bit I want to talk to you guys about with this problem. So with this, we're assuming that the clock was started right when so let's draw a mass on a spring real quick, and then it's stretched out to there. We're imagining that the clock was started when the mass on a spring was out here at its maximum amplitude. But what if we didn't quite start the clock then? What if we didn't start the clock until this block was at its equilibrium position there? So we want to rewrite the position as a function of time, and we want to replot the function. So what would that mean? Well, let's take a look back at our position function. Well, what would that mean is we want to shift this whole thing to the left, because instead of starting the clock here, we're starting it here. So we want this point to be at time 0. So on your formula sheet, the unofficial one I gave you, not the official one on the AP exam, remember there's also this formula for expressing the position of an oscillating object as a function of time. And remember, this thing here was called the phase angle, pronounced phi or phi. So a positive phi will shift the cosine function to the left, and a negative phi will shift the cosine function to the right. So basically, what we want to do is we want to shift this by 1/4 of a cycle. So a full cycle is equal to 2 pi. Divide that by 4. And we want to shift it by pi over 2. So we just want to rewrite this function, shifting it to the left. So our new function is going to be 0.1 times the cosine of 15t plus pi over 2. Now, if we wanted to shift it to the right, we would want to plug in a negative phi. So let's take a look to see if this is actually correct. And I actually graphed it on Desmos here. So this top red function is what the original function is. And look, it looks very much like the one I drew, a little bit neater. And, you know, it is at, the period is at 0.419 here. So it is a little bit after the 0.4 on this graph. And then here what I have is 1 plus 1.5708. That's equal to pi over 2. That's how much I wanted to shift it by. So that's this green line here. So notice that it does indeed start at the equilibrium position. So I did just end up shifting the red function to the left by adding in that phase angle. So that phase angle is just basically when you start the clock. I think that's why they don't include the phase angle on the official formula sheet, because it doesn't really matter all that much. The shape of the graph is still going to be the same no matter what the phase angle is. It's just kind of where you actually start the graph. That's what the phase angle means.